Hi, my name is Shaofeng. Today I'm going to introduce our new work in ICCV'25. The name is ToolVQA, a dataset for multi-step reasoning VQA with external tools. In recent years, integrating external tools in large foundation models is a promising way to build versatile AI assistants. By leveraging external tools, LLMs can break down complex tasks into smaller, more manageable subtasks. Here is an instance. The input is how old is the beer brand in the picture, and the tool can decompose the task into three subtasks. The first one is object detection. It can detect the beer in the image, and the second one is the OCR. It can recognize the brand name of the beer. The third one is the search engine. It can search for beer brand information. Through the study of real user logs, we found that real-world tool use often involves real-world scenarios, complex visual scenarios with real-world context. For example, real-taken photos rather than synthetic images. 2. Real-world queries. Challenging queries with implicit multi-step reasoning process. However, existing datasets often lack these two critical properties. First, the scenarios are synthesized instead of real-taken. For example, in the left, the apples equation and the text are the synthetic scenarios, resulting in overly simple scenes that do not align with real-world scenarios. 2. The queries require only single-step reasoning or explicitly provide hints about the reasoning process. For example, here says I'm using the cheap YouTube API tool. To overcome the limitations of existing VQA datasets, ToolEngine introduces an automated data generation framework that simulates the human problem-solving process. It contains three core designs. The first one is image-guided depth-first search. On a multimodal tool graph, the system adopts a DFS to sequentially select and invoke tools while performing actual reasoning operations. Each step involves not only selecting the appropriate tool, but also constructing parameters and parsing the output, thereby generating a logically coherent and goal-oriented reasoning trajectory. The second design is the question and answer construction mechanism. To ensure that each query exhibits implicit multi-step reasoning and real-world contextual relevance, ToolVQA enforces strict constraints so that questions do not directly reveal reasoning loops. Meanwhile, the final answer must come from the result of the last two innovation, rather than from general image descriptions or common sense completion, making the tool calls necessary. The third design is an example matching mechanism based on dynamic program. ToolVQA introduces a dynamic matching program based on the longest common subsequence to overcome the limitations of template-based approaches in generating diverse reasoning paths. The system selects multiple reference examples most relevant to the current trajectory from expert-constructed typical human use cases. These references then guide the next tool selection and parameter generation, enabling more flexible and human-like reasoning processes. So we use ToolEngine to build ToolVQA, a tool reasoning and VQA dataset. Here is some statistics of the ToolVQA dataset. We derived the tool use frequency from real-world user study, ensuring both practical and necessary. And we further do some fine-tuning experience on the ToolVQA dataset. We cover three model settings, and we test major models including GPT-4o, GPT-3.5, Cloud 3.5, Queen 2, Lava. We use step-level metrics to comprehensively assess instruction following and tool selection accuracy and answer summarization accuracy. We found that the fine-tuned Lava 7B model surpasses the closed-source GPT-3.5 Turbo model on the test set. We further found that the fine-tuned model demonstrates strong generalization ability on out-of-distribution datasets such as text VQA, TeleQA, InfoSeq, GTA, and TempLemma, consistently outperforming GPT-3.5 Turbo. And few-shot experiments further show that the fine-tuned model on ToolVQA continues to benefit from few-shot examples, effectively leveraging in-context learnings to enhance reasoning and answer accuracy. And at last, we do error analysis. We found two major types of errors. The first type is parameter prediction errors. The model frequently omits critical information when constructing tool parameters, leading to incorrect or incomplete tool innovations. The second one is the answer summary errors. Even when the tool returns correct results, the model may select or aggregate the information incorrectly, producing a wrong final answer. So here is the conclusion of this paper. First, we present ToolVQA, a large multimodal dataset for real-world tool augmented reasoning. Second, using our ToolEngine pipeline, we generate 23K real-world examples with implicit multi-step reasoning over 10 tools and 7 domains. Third, experiments show that Lava 7B fine-tuned on ToolVQA not only excels on the in-domain test, but also outperforms GPT-3.5 on 5 out of distribution benchmarks. Fourth, ToolVQA serves as both a benchmark and a training ground for developing more capable, generalizable tool-using agents. Okay, that's all. Thank you. For more information, please check our QR code. We have already released our full dataset, our code, and our project page online for the future works. Thank you.